Hello, I welcome you all to Heathrow. So, in this video, we will learn about consistent hashing, why it is in a place, why it is used, what was our problem in a horizontal scaling that we need to use consistent hashing. This is a kind of system design problem. So, uh, develop any app or any software. At early stage, there are no more users. You can handle it. I mean, there is a client, one client, and server serves it. It's not a complex architecture. You can understand client is your browser or maybe any mobile application, and server is a remote server hosted on a cloud. So basically, your client sends request to server, server interact with database, gets its response back, and show a response to you. And the client formats it. Some I works like a pretty fire and shows you a response. And suppose your app becomes famous and there are many users, and there are many users now to your applications. Users are in millions. How are you going to handle such a big volume of traffic? So traffic increases, so you have two options: vertical scaling and horizontal scaling. What do we mean by vertical scaling? Vertical scaling is nothing but giving more power to your machine, single machine. We provide more resources like increase 64, use 64 core CPU. Earlier, if you were using 8 GB RAM, let's use 32 GB of RAM, and likewise. I'm just saying random numbers. So, vertical scaling, you provide a power to a single machine. But there are many downsides to vertical scaling. It is mostly suitable nowadays. Machines are so powerful that your common, or I mean, if there is not a huge user base, you can go with the vertical scaling. Practically, many applications can be uh, deployed on a single machine and they work well. But we are talking about here in horizontal scaling, we are talking about scale which is such a humongous that take example of YouTube, LinkedIn, or many famous any your Ola, Uber, or Zomato, Swiggy, such food delivery apps. Here, user base is just goes wild, and you cannot handle it on a single machine. So let's see some downsides of vertical scaling. So you can't scale forever. I mean, there is a practical limit to how much max RAM, CPU can there will be on a single machine. And here we find a single point of failure. I mean, one machine, one failure. If by any chance, by any unforeseen circumstances, that machine fails, then your website is a down. So scaling up needs server restart. You yes, tomorrow you want to scale your application. I mean, you want to increase your resources. Then how are you going to change that hardware? You need to shut down your machine, and ultimately your website will be down. VM resize, maintenance window, higher hardware cost. One machine can handle limited concurrent request. So one machine can have limited threads. CPU context switching become bottleneck. I mean, one CPU cannot handle such a huge amount of requests simultaneously, concurrently. So there are many limitations to vertical scaling. So better option is horizontal scaling. Here, instead of providing more resources to single machine, we keep adding more machines. And so positive sides are high availability, no single point of failure, because now your load is distributed amongst multiple machines. I mean, like this. Instead of single server in horizontal scaling, you deploy your applications, multiple instances of your servers or databases or caches. You distribute all things instead of hosting them on a single machine. So this is how your horizontal scaling looks like. So in horizontal scaling, you have high availability because if any machine goes down, other two can serve your requests. No single point of failure, obvious, because there are your application keeps serving request even if some of the machines fail. And limited scaling. I mean, practically you can keep on adding as many servers as you want, and you can place them geographically closer to your clients, and this way you reduce latency. So, and anytime you are scaling or upgrading your software, you can upgrade it or scale add dynamically other servers to this cluster, and you don't need to shut down your application. You can smoothly add or remove servers as and when needed, and your application, your clients or your users won't see any downtime or maintenance mode, etc. This is cost effective. If you have used AWS, you are billed as you use it. I mean, if you are using 4 GB of RAM, or how many requests what is the traffic of your website, depending on that, you get billed on AWS. And better parallelism. Uh, what do we mean by better parallelism? Multiple computers or machines can handle high volume of requests simultaneously. So because load is distributed, load balancer distributes evenly. We ensure load balancer has such algorithms in place that requests go to all the three servers evenly. I mean, no server is sitting idle and one is under the immense load. We avoid such situations. So yeah, these are the positive sides of horizontal scaling, but it's not that easy. Horizontal scaling also has its own cons, or I would say trickier parts, but most of them are solved. As of now, we have solved. I mean, in one of the problem was which server will handle which request or data. I mean, if your application is stateless, and most of the REST APIs are stateless, and in that case it is much simpler. But again, if you are using caches, if you are have sticky sessions, I mean, you have a session data maintained on your server side, or your database is a sharded. Sharding is a concept, again, one concept in scaling. When you have a huge data, you have huge database, and you cannot store it on a single machine, so you tier that table. I mean, tier means we keep some few thousand or millions rows, first thousand rows on this, for example, server, this machine, and we the rest of the rows from 1000 to later 2000 on another machine. Hypothetically, 1000 is a limit of one machine. So this way we divide our database and it's called as sharding. But in such scenarios, then the situation is like you have to send same request to same server. If I am logged in to this server, server 0, and there is a session method on server side, and my second request goes to server 1, then I may see I am logged out, please log in. I may abruptly get logged out. I mean, here I will not have any session. Or same with the caches. If you have a distributed cache, then application need to remember which key is stored in which machine, I mean, which instance. If there are multiple instances of cache, distributed cache, then we need to decide which key should go in which cache. And while fetching also, we need to remember from which instance we need to get the value from. So here I have written it down. I will provide these notes to you. If we distribute cache, we need to put same key in the same instance and page, or if we have db shards. Otherwise what will happen? Cache miss, abrupt logouts, etc. So earlier, what people followed, naive approach, we are calling it. So earlier, what people thought, let's hash the user ID using any MD5 or SHA algorithms. Or there are many hashing algorithms out there. Using that algorithm, we will hash user ID or IP address. Suppose we hash IP address from which request is coming. We hash that IP address, and then find a modulo with the number of servers. Now the number of servers is 3. So suppose IP address is 12.3.1.2 something like that, and we take a hash of it. We perform hash operation on it. Then we get suppose this as a output, and to this hash we will find a modulo using percent 3. 3 is a number of servers. Here I have 3 servers, so I find modulo of 3, and I get a output as a 0. So this is considered as index of server. And as I got a 0 here, I will assign this request to server 0. Then all the requests coming from this IP, I will get the same hash. Hash function has some characteristics, like it is deterministic. Same input gives same output always. That's mandatory. So if the same request comes from same IP, again I will get the same hash, find a modulo, and using that index I will route that request to that particular server 0. This way I am ensuring that all the requests from that client are going to server 0, and he may not face a session loss. Or same goes with the cache. Okay, so this was an IO approach, but as you can see that this modulo is highly coupled with this 3: number of servers in my cluster, or number of database instances, or number of cache instances, whatever it may be. So in this way it works fine, but in a practical, in a real scenarios, we need to scale up and scale down applications. Suppose there is a Diwali sale on Amazon, then there might be a need of more servers in a cluster because more users will rush to Amazon website. In that scenario, suppose I change this from 3 to let's say 7 servers. Okay, so again the request come from same IP address, I will get the same hash, but this time I am using 7 servers, so modulo 7, so we get index 6. Okay, so we will then the request from this IP will go to the server number 7th. I index 6 means server 7th, 6th, whichever server will be there on 6th index, request will go to it. Then there will be no session for that corresponding user, and he may see as a session, uh, I mean session loss. He may need to log in again, because earlier his request was going to a server 0, but now it's going to a server 6th. Same happens with the cache. If we are storing some index, some, let's say some, there is a key we are storing in a cache. For example, let's consider I am storing Rohit as a key. Okay, so I will hash it, hash the key. It will give me some random number, and I was earlier finding a modulo with a 3. So what will be the output? 0. So again I will put that key in the cache at index 0. But in future I add one more server, and say number of not a server, one more cache instance, and I want to search the same key. I want to fetch the key from the cache. So I will hash the this key Rohit. I will get 345 same hash, and then modulo I will find with the 4. Then what will be the index? Similarly, if I increase the number of cache instances to 4, and I want to fetch that key Rohit from the cache, and then I will find a modulo with a percent 4. So in this case I will get index 1, and earlier I was trying to save it in index 0, but now while fetching, it will try to find the key from instance at index 1, cache instance with the index 1, but there it won't find it, and we will see a cache hit, and it will increase unnecessary DB operations. Okay, so now you will get idea that why the naive approach is not good in practical scenarios, because module is dependent on number of servers, so work well for fixed cluster, but dynamic scaling we need to add remove servers. So solution to this was a consistent hashing. What we do in a consistent hashing is we take a one hypothetical. I mean, this is not a physically present on any machine, or it's just programmatically we are solving this problem. Let's consider one virtual hash space of a 32-bit. So we will have range from 0 to 2 raised to 32. So this will be our range. On this hash space we will map our keys and servers using the same algorithm. Whatever algorithm that will be used to hash servers will be used to hash keys also. Okay, so we can wrap it and imagine it at a circle also, from 0 to 2 raised to 32. 32. So we call it a hash ring. Okay, virtual hash ring. And suppose we have key 1 whose hash is 100, server 1 whose hash is 500, server 2 whose hash is 700. So let's first map our servers on a key, on a hash space. So suppose I put server 1 here 500, server 2 here 700, and while uh, and also we keep the keys on the hash space at respective positions like 100, 600. So how do we decide which key resides on which server, or which request is handled by which server? So we go clockwise, and whichever server comes first, we consider that key will be stored, or that request will be handled by that particular server. Here from 100 we go on increasing order, basically here from left to right, and we find server 1. So we will assign that 100 key 1 to this cache instance, or that request from particular IP address or user will be routed to a server 1. Similarly, key 2 is a hash is 600. We go in ascending order or clockwise manner, and whichever server comes first, we will assign key to it. So here, how do we solve the problem of reshuffling? Okay, So here, what was the problem? If the number of servers changes, we need to change modulo dependent. We need to change which key is assigned to which server. There will be a lot of key reshuffling. We need to change that earlier. Suppose earlier that request was handled by server 0, now it will be handled by server 1 or server 7. This way we need to shuffle a lot of keys. So instead of that, here we need to shuffle only a part of a keys, I mean a very small part of a keys. So if tomorrow I add one more server here, server 3, whose hash is uh, 650. Okay, so by if I add this server, I just need to reassign a key 2. Instead of this, I need to assign it here. Key 2 600 will now be assigned to server 3 instead of server 2, cause from 600 650 comes first when we go clockwise. So we key 1, we need not change key 1 here, just changing key 2 suffice. So this way we avoided a problem which we faced in naive approach. Or suppose tomorrow we remove this server 2, server 2 is removed. In that case, we need not to change all the reshuffle all keys, we just need to change this 100. Okay, we just need to we will go from key 1 to clockwise and see which server comes first. We will see 600, so we will assign that to 600. This key will be assigned to 600. This way consistent hashing helps us. It reduces cache misses and overhead of reassigning the keys. Let me explain you problem in naive approach with help of this table. So these are the keys: John, Sam, Sundar, Satya, and their hashes are 1 2 3 2 2 4 7 8 9. Okay, and earlier, let's suppose there are two servers. 2 is number of servers, so we take a modulo. Here we get 1, here 0 1. So we assign it to as John to server 1, Sam to server 0, and likewise. And now if we add one more server, then we will get the same hash for the same keys, but now the modulo will change. For John, server 0, earlier it was on server 1. We need to reshuffle that data. Here, Sam, server 2, earlier it was on server 0, now on server 2, and rest 2 on server 0. Here we can see that server 1 was unassigned. It is idle and load goes to server 0. So this is not even data distribution, and also we need to reshuffle all the keys, otherwise it will be seen as a data loss or cache miss, session miss, the session loss. These kind of things will happen here. So this was a problem with the naive approach, and with the consistent hashing we solved it. Why? One more question I have mentioned here. Why we hash the keys in first place? So hashing gives us uniform distribution, deterministic mapping, same input, same output, same server. This is critical for caches, sharding, sessions. If we hash a user id, some number, so basically if any data type, if you hash a string or any other kind of key, string, number, object, you will get fixed numeric space. Hash gives us some random but fixed length number. Okay, so into fixed numeric space. So what it helps us in mapping, cause we will map servers on the same number hash space, and the keys also on a same hash space. So it helps us in comparing the hash keys of the server and hash keys of the keys. So without hashing, mapping would become random and inconsistent. Okay, then this is again a hash key consistent hashing concept. This is our hash space and we assigned it to servers. Okay, in real systems, here you might have seen one more problem. Suppose we remove server 3, for some reason it's down. Okay, then you can see all the key 2, key 3 will be assigned to server 2 only. Okay, so load goes on, whole load goes on server 2. And if there was another server, 4, it is idle, I mean it's not assigned there. This is not a even load distribution. So avoid it. In a real scenarios, we use virtual node. I mean, in virtual, by virtual node we mean that instead of mapping server 1 or server 2 at just single one place on this, we take a hash of suppose server 1 underscore a. Okay, we take a hash of server 1 underscore a And similarly for server and map it. Suppose it gave us value of 100. We again map, we again hash server 1 underscore b. We give some random values here and again hash for specific number of how many virtual nodes we want of a specific server. One, there will be one real machine, I mean physical server, and we will map it on multiple places on a hash ring. Number will be determined by us, I mean more the virtual nodes, more the even distribution of data. You will see why. I got 700, and hash server again 1 underscore c, I got 800. So this way I will map server 1 on these many places on this ring. Server 1 server, let's map one server at 3 places. Similarly server 2 will be mapped on 3 places. Server 2, server 2. So this way, um, what happens, we get a even distribution of data, and we ensure that not all keys are assigned to one specific server and other one is sitting idle. Like here server 4 has not got any keys, but had we used virtual nodes, we would have mapped server 4 here also, server 4 here also. Same goes with the server 2 and server 1 also. So we will have distributed key 1 on server 4 and 2 and 3 on server 4, and remaining keys on remaining servers. This way we can evenly distribute the data. So this is the concept of virtual node. Servers may not evenly distributed. One server may get too many keys. These were the problems. So in virtual node, server A, one position, we do server A1, A2, A3. Likewise, we hash multiple time one server, and this way uh, load spreads smoothly. If one server goes down, load spreads smoothly. One simple analogy to consistent hashing is, think of a clock. Servers are number of clocks. Keys are also numbers. Each keys go to the next number on the clock. There is one code which implement this consistent hashing using a tree map. I will explain it in some other video. And there are some characteristic of a hash function also. We'll see them later. Deterministic, uniform distribution, low collision, it etc. That's it for this video, guys. I thank you all.